Okay. Well, let us then solve these equations first and then use them to the exercise that I am going to post in a moment. So, how do we do that? So, pi 1 can be written in terms of pi 0. Since pi 2 is written in terms of pi 1, we can just plug this pi 1, right? Just to get something in terms of pi 0. So, this is pi 0 times q0. Now, there is q1 here. I have q0 times q1, right? And for pi 3, then you will have actually pi 0 times q0, q1, and q2, right? And finally, when you even this also is, these are all alike, and we can just write the entire thing as pi 0 times, starting from q0, then you have q1 up to where? When it is 2, you get 1 here, right? When it was 1, it was 0, then it is just 1 less the index that you have on the right, on the left. So you have n minus 2, right? Qn minus 2. And now we were able to express pi 1, pi 2 through pi n minus 1 in terms of all pi 0 times something, right? And now we can use this equation to find the only unknown that is left, that is pi 0, right? So at this part, we were able to write all variables in terms of pi 0, right? So there is then only one unknown left. We can use either this equation or that actually to find pi 0 after we plug in pi 1, pi 2 through pi n minus 2, all these expressions that we found. I guess this is easier to go with, right? So 1 equals pi 0 plus pi 1 and so on, pi n minus 1. And here, pi 0 is the same. And pi 0 is common to all of these terms, so we can just take into common parentheses. There is 1 coming from here, and pi 1 was pi 0 times q0 only, so I have q0 here, and pi 2 was this, so I have only this 2 that I have to account for, and then for pi n minus 1, I have this part, right? Namely q0 times q1 and so on times qn minus 2, right? We can write this in a more compact way, right? This is the sum of products, right? So you have 1 plus the sum, and sum goes from 1 to n minus 1, okay, 1 to n minus 1, of what? You multiply q sub k, let's say, k starts from 0, right, goes till I minus 1, right? When pi 1 equals pi 0, well, pi 1 equals pi 0 times q0, right, you have only q0, so this is I equals 1, minus 1 gives you 0, right? The product goes from 0 to 0, so this works. This is working, okay? We have that. And now we can calculate pi 0, right? From this, we know that pi 0 equals 1 over 1 plus the sum as I goes from 1 to n minus 1, the products of qk's as k changes from 0 to I minus 1. Okay? Since now we know what pi 0 is, we can now find all other pi's. So the pi I then equals, right, this pi 0 times one of these terms. And that is what? So product of qk's as k changes from 0 to I minus 1, right? When it is n minus 2, you have n minus 3, the last term, right? And then you divide, of course, by this quantity, which is 1 plus. So let me change this I to another dummy variable j. J going from 1 to n minus 1. We sum the product of q. My k doesn't hurt in this place, I guess. So we can just leave it like this. Okay. This is true for every I, 1 through n minus 1. Right? For I equals 0, we have this expression, so we have the entire probability stationary probability distribution identified. All right, and so anything, any quantity that we are interested in the long run, we know they are related or can be calculated by using this stationary distribution, right? For example, now we can think about the performance of a given, or how we can quantify the performance of a given H replacement policy. Okay, let me see. Okay, intuitively, right? Intuitively, now you know that where is the chain? I guess I can just look at this one before I write anything else, right? Here. Now we have the transition diagram of the H process when you decide to implement an H replacement policy with Hn, right? So every time chain gets to state 0, you know that actually a new component has just been installed, right? Then actually the fraction of the time you spend in time 0 also corresponds to the fraction of the time when you make a replacement, right? So the pi 0, namely this quantity, gives you the fraction of the time actually the person who is taking care of the system is busy with replacing the component, right? And some of these replacements are due to in-service failures, and the others are due to plant replacement, right? H replacement, right? So they are all counted here, so we cannot distinguish that by just looking at what pi 0 is. But what do you think that the fraction of the time when we make a plant replacement? What is the long-run fraction of the time when you know that you make a plant H replacement? Pi n minus 1. Why? Because every time you get into state n minus 1, you know that there is one component up and running, and it's just, right, in the next period it is going to be of Hn, and therefore you are going to replace it, right? Okay. And then the difference between pi 0 and pi n minus 1 is going to give us what? Right. So they are going to give us actually the replacement due to an in-service, right? The ugly replacements, or the replacement because of an ugly reason, because components actually fail while they are in service, right? So let us take notes of them. So pi 0 is nothing but the fraction of time when a replacement takes place, right? And a pi n minus 1 is actually the fraction of time when a plant replacement takes place, right? And if you look at the difference, right, this should give you the fraction of time when an in-service failure happens. Right? Then if this is too large, then that means the system is actually causing a lot of inconvenience to its users, and then you will want to reconsider the replacement policy, right? If this is too large, then the serviceability of the system is not great. People will all the time complain. Students will all line up in front of the servicemen asking for their lost files and things like that, right? If the university doesn't want to take chances, then it is better to do what? Most likely you would just decrease n, right? You will actually replace components more often before they actually fail during the service. Alright? And we know how we can calculate those things. Do we know them? Actually not quite. So what are these QKs and things? We know more or less what they are. We can actually simplify them even more. And perhaps we can do that now. Right? And you remember that at the beginning we decided to use capital AI for the sum, right? AI plus AI plus 1 and so on. And using this, we wrote for QK, right? So here I have QK. What was it? A K plus 2 divided by AK plus 1. Right? I have this. Right? And then this is then going to actually simplify a bit. Right? So what is this? The first term is Q1, right? For K equals 1, you get what? Is it A3? Well, sorry. For K equals 0, you get Q0. When K equals 0, you get A2 divided by A1, right? And then the next thing is going to be K. For K equals 1, you have Q1, which is for 1, you have A3 divided by A2, right? So they cancel. But in the meantime, it just goes like this till when? The last term is going to be for K equals I minus 1. For K equals I minus 1, you have a I plus 1. And here a sum I only. Right? And this is supposed to cancel with the term that is just to the right of it. And just before this, there will be another term for which this thing will actually disappear. And you get what? You get a I plus 1 divided by, is it A1? Okay. And this is now sum from 1 to n minus 1. Right? So for I equals 1, you get A2. Right? Maybe I shouldn't touch that, but let's just now operate a little bit more and simplify these things. The pi 0 becomes what? So it is 1 over 1 plus the sum. As k goes from 0 to n minus 1, right? Of what type of numbers? You have ak plus 1 divided by a1. What is a1 in the meantime? Do you know what a1 is? So if we just use this, a1 equals small a1 plus a2 plus and so on, right? And the age of the smallest age a component can take was what? It is here actually. We start from 1, right? And if ak is supposed to be probability mass function, the sum of all these a's. So this a1 equals to a1 plus a2 and so on and so forth. What is this? This is the probability that t is finite, which we take it as 1. So it's just a legitimate probability mass function. A1 equals 1. Right? It is the sum of all the mass, all the probabilities for the ages that this random variable t can take as a value. Right? So actually this is 1. So we have 1 here. We have the sum like this. And what is this? This starts like from A1, right? Goes till AN, right? So we can actually again write it like this in a simpler way, right? Huh? Have I made a mistake? It is important that we don't make any mistakes. Is it A1 really? If we start from 1 to n minus 1. And this is indeed ai plus 1, right? Or maybe I should check my own calculation. This is... is there something wrong here? I am getting a different number. Oh no, it is... The sum starts from 1, right? There I made a mistake. I mixed this with this sum. So the original sum, so this thing equals to this, and we said that this is 1, so we can forget about that. But the sum goes from 1 to n minus 1, from 1 to n minus 1 of what? AK plus 1, right? I happen to change I to k, but that's fine, right? As I go back and forth between two boards, I guess I mix them. So if I just write them and expand this sum, I get what? So I have A2, right, plus till A n, right? But we said this is the same as A1, right? We can just compactly write everything as the sum 1 over the sum, right? A1 to an, if you wish. Okay? If you wish. And then this, so that was the simplification for pi 0. We can do something similar for this one. Of course, the denominator looks like the denominator of pi 0. And we also found something for this, right? We said this is nothing but ai plus 1, right? That was exactly what I calculated here. From 0 to I plus 1, that turned out to be ai plus 1. So pi I, right, equals ai plus 1 divided by a1 plus everything up to n equal to an. So this is true, first of all, for I equals 1 to up to n minus 1, right? I equals n minus 1. But look, when I equals 0, we know that this is the formula that we use. But if I said I equals 0, so I get a 1, which is 1, which is the same as this one. So actually this single formula just covers all of them. Right? So we have that. Okay. Things simplified. So just to write everything in a compact form in this same place. So this is AI. So if it is AI, we start from I. And just to remind ourselves the meaning of this, this was nothing but the probability that a typical component is going to have an age at least as large as I. Okay? We have that. Okay? Then, all right, we can just plug these numbers here to find the fraction of time when an undesirable in-service failure happens. Okay? Or the fraction of time when this happens. Okay. And then in none of these discussions, actually, we did not pay attention to the costs, right? So we said, okay, in-service failures are undesirable, therefore we should avoid them. But in order to avoid them completely, then you should actually replace all the components almost instantaneously, which is not realistic, of course. So there is always a kind of trade-off between how much inconvenience to the users of the system is tolerable, and how much money you can afford to replace things quite often, right? In order to solve such decision problems, then you have to actually give costs and quantify each one of these undesirable costs of all these undesirable outcomes. Right? There are two things, right? So in general, right, we know that, okay, the replacement of in-service failures are more expensive, right? The in-service are more expensive. Replacements of in-service failures are more expensive than those of plant replacements. Okay. All right. And in this case, by planned replacement, we of course mean the age replacement. That's what we are studying at the moment. Right? For example, if you denote by C, okay, the cost of a planned replacement right? Now you may then have to pay an additional K units, K monetary units, whatever that is, when an unplanned in-service failure happens. Okay, and when you have to actually make an unplanned replacement because of an in-service failure. Okay, so that is denoted by K, the additional cost of a replacement due to an in-service failure. Okay. Actually, in the last year, I guess this happened 3 times to me. I lost one hard disk, one motherboard, and then another hard disk, and all of them were the new. And the computer was actually under warranty, but that doesn't help. Of course, it doesn't just bring your data back. Well, this doesn't apply for it on an individual basis, of course. But if you have enough money, maybe it's a wise thing to change even your computer every year. In that sense. Okay, now we have this cost structure here, and let us try to quantify the long run expected average cost per unit time. Right? So every time you find yourself in state n-1, you know that you are incurring this cost, C, because it is a plan. You expected this would happen to you. Right? Every time a failure happens between when the system was in this state, when it was coming to this state from any other state other than this one, right? And then you will pay C plus K, right? This is additional K units. So we have the cost structure. Now I would like to find, so forget about that. Let's calculate the long run. Okay, expected average, long run expected average cost per time unit. Maybe we can be more specific. It's expected average maintenance cost, right? Per time unit. Okay. So the answer that you should expect, what is that? Can somebody tell me? Can you guess? Or you, using your intuition, I guess you should be able to spell out what the answer should be in this case. In terms of pies, right? You take bunch of pies, multiply with bunch of numbers, you will sum, divide, I don't know. Do something with it. Alto. What is it? How much should I ask for maintenance on average? Pi n minus 1 times C. So what is this?
Planned replacement cost.
Okay, per time unit, right?
Plus C pi 0 minus pi n minus 1.
Oh, too long. Let me just do it like this. C times pi n minus 1 plus,
In parentheses, pi 0
right,
minus pi n minus 1.
okay,
Times, in parentheses, C plus K.
okay, that's great. But you should explain us. What is this? Right. So this is the fraction of time when you have to make a replacement because an in-service failure happened. Right? We said this is okay. The fraction of time when you make a planned replacement, and this is the fraction of time you make a replacement, the difference has to give us, right? We discussed it actually, that's already on blackboard, whiteboard, whatever, right? So this is the fraction of time when you are gonna incur more maintenance costs because actually you needed to replace the thing while it was really in service, right? And therefore you have to pay this additional cost on top of C. Right, so we are done with it, right? But we can actually go through and take a little bit, we can think a little bit more. You remember how the long run averages can be written explicitly, and then when you take the limit, how we actually arrive at this pi quantity. So we can do actually the same exercise and see whether what we just wrote on blackboard is consistent with that calculation as well. So that perhaps those of you who couldn't see this right away can now understand better what is going on. So every time, right? Every time n, when the age of the system, right, at time n is I, and when the age of the system at the next time period equals 0, right, when this becomes 1, then what is going to happen? That means that there is a replacement, right? Because in one period, the state of the system, the age of the system goes from I to 0, right? 0 means fresh quantity is in place, right, at time n plus 1, and you are coming from state I. From where you are coming will now determine how much cost you are going to incur. If I is less than n minus 1, then this failure must have happened while the system or while the component was in service. Therefore, we are going to pay C plus K, right? As I said, this happens when I is between 0 and n minus 2, okay, and or you will pay only C if I equals n minus 1 at time n. Well, at time n the state of the system or the age of the component is n minus 1, and at time n1 plus 1 as before it becomes 0. There is no a planned replacement. Therefore, you pay only cost C, right? So that is what happens at time as the process moves from time n to n plus 1, right? Well, why did I use n? Well, that's fine. You can use k this time. So when I sum from all these quantities for n equals 0 to k minus 1, what is k? That's also not nice. Let me use m minus 1. So this gives me what? The total cost in the next m periods. The total maintenance cost in the next m periods. It's a random variable. We divide this by m. Now I have what? The average cost, average maintenance cost over the next m periods. If I take expected value, now I have expected average cost in the next m periods, right? Across the next m periods. But I am not really interested in for this cost for any particular m because I cannot differentiate which m is important anyway, right? Rather, maybe it makes more sense to look at this quantity for large m when the system sort of reaches the equilibrium state. Then what is this cost? That's exactly what, as before, long run, right? Expected average, right? Maintenance cost per time unit. Right? That's exactly what I want to calculate. Right? So I just wrote it in terms of random variables. Right? Now, if everything that we learned by now is correct, then this should equal this one. Right? Well, let us check. Right? Let us check whether that is the case. Okay? So this equals to what? Now, sum of the sum, which one? Let me see. This sum doesn't depend on n or actually m, right? We can just take this sum all the way out, and all these constants we can also pull them out, right? And we can just rearrange this thing like, okay, c plus k, right, times, perhaps, okay, let me take this sum over I as I changes from 0 to n minus 2. Then I have limit expected value and the averages. So limit as m goes to infinity. Inside expectation, I have 1 over m times the sum as m goes to 0 to m minus 1. What? Is indicator in the variables now. Which is, now I can write it more explicitly like indicator random variable of the event that xn equals I and xn plus 1 equals 0, right? So we can just break this expectation, summation, expectation at this sum. So this is 1. And for the second term, I have only c times, I don't even have a sum. I have just the limit as m goes to infinity, expected value of, what do I have? 1 over m, right? The sum goes over n. So I have to keep that inside expectation. I don't, well, for the time being at least. Okay. And then this one. The indicator. Now let me write it in a more recognizable form, right? Indicate random variable for the event that xn equals state n minus 1 and xn plus 1 next period, the age, in other words, of the process just becomes 0, right? I replace that. And there is a sum here. We shouldn't forget that. Okay. All right. Now, before I take the limit, let us take a look at this one. What is this? Actually, I can take the expectation inside, right? The expected value of this constant, it can also be taken outside, right? And then you have expected value of sum of random variables. It is the same as the sum of expected value of the random variables. The usual game, right? So then you have c plus k, right? So this sum is over the state space, so I'm not going to touch it for the time being. So then, okay, I have the limit as m goes to infinity, 1 over m times sum. Now I take sum outside and the expectation inside. Expected value of indicator random variable is the same as the probability of the event sitting here. Okay, let me write it one more time. Right? I have that. And then I have plus c times, right, the limit as m goes to infinity. This 1 over m, we can take it out, summation, we can take that out as well. The expected value of this time, this indicator random variable. Right, I have that, which is actually just the same thing except I is now a concrete number. Right? So what is this? We can just again use the Markov property, right? This is the same as we can condition on this. Probability that at time and the age of the process equals I times in one step the age goes from 0 to 1. Right? From I to 0. What am I saying? I am also tired, I guess. Pi0 is what? One step transition probability, which happens to be pi, right? The small pi. May I write it right away like this? Remember from the diagram, we call pi the probability that goes all the way down to state 0. And how about that? Well, we have the same thing, right? So this is the probability that at time and the age of the process now equals n minus 1. And given that the state of the process at time n equals n minus 1, what is the probability that at the next period the state is going to be 0? One step transition probability for going from state n minus 1 to 0, which is, well, of course, Pn minus 1 again, for this model, for this replacement model. So we should now simplify things and see what happens. Okay. Right, so you see P1, P1, okay, what is this? Maybe I can erase it, huh? Pn minus 1, what is that? It is 1. Actually, we know that it is a simple number. Okay. Okay, I'm going to erase this. Right, and then, okay, let's simplify things, and then we'll be able to see the result easier. C plus K times, what do I have there? Sum over the states 0, 2, and minus 2, right? Then we have the limit, right, as m goes to infinity, 1 over m times the sum, right, as n goes from 0 to m minus 1, the probability that at time n the state of the process equals I, right, and the number pi, right, doesn't depend on m, so we can just write it outside. And look at this limit first and then multiply the result with pi later. And then in the second term, we don't have a sum, in fact, right? It is c times just the limit as m goes to infinity, 1 over n times the sum as n goes from 0 to m minus 1. The probability that xn equals now a fixed state, right? It is n minus 1. And there is Pn minus 1, we just realized that it is 1, therefore it is already there, so it's taken care of. But then we already noticed that this chain X is regular, therefore it has stationary probability distribution. We calculated them, right? And we know under these circumstances, right, whether this is conditioned on the initial state or not, this thing converges to, right, fraction of time spent by this chain in state I. And it is the same for this one. So this is the same as pi, right? The fraction of time spent by this chain in state n minus 1. It's the pi n minus 1. Right? And then we can now further simplify the expression. This is c plus k times, right, n minus 2. I equals 0, so this is pi I times, why don't I just go back and use the one-state transition probability? I guess that's going to help us better to see what happens next, right? So pi was the probability of going from state I to state 0 in one step, right? And plus, from here, what do I get? C times just pi n minus 1, that's all. Right? Now see, this looks very familiar, does it? This is one of the right-hand side of one of the equations this is very similar to the right-hand side of one of the equations satisfied by the stationary distribution. You would say? So it is almost pi 0, right? Because of this, right? But that would be true if this was just going through all the state space, but one of them is missing. This goes all the way up, only n minus 2. Where is n minus 1? Right, the one that you remember, okay, the pi 0 equals, right, sum pi I times pi 0 when I changes in state space. In this case, state space is from 0 to n minus 1. That one is missing. But we can add and subtract. Right? Let's just do that. So pi 0, what do I need? I should add pi, right? I must add pi n minus 1 times 1. This is 1. We know that this is 1. Exactly. So you added that, therefore you got pi 0. Now you have to subtract it in order to keep things in balance. We have that. So let me just erase this. So we know what this is now. Therefore we can now simplify things. C plus k times pi 0 minus pi n minus 1 plus c times pi n minus 1. And is this the same as what Gizem suggested before? I guess it is the same, right? So, okay. I am not going to, of course, insist on going through this exercise every time I ask you to calculate the long run expected cost, unless you can write this down right away. If you are having trouble figuring out what this is, then at least you have it. No, it's easy. Well, there are 1 or 2 people. Okay, that's fine. And you cannot talk for everybody. So, in case, and you don't know what problem you will encounter in next time. So, it's just keep in mind that you should be able to at least go through something like this, an exercise like this, in order to figure out. But that's great if you can write these things easily. Now we can further simplify this, right? How can I do that? Alright, so this one is common there, so let's just take that out. Then there is one of them common, so there will be minus, I guess, k times pi n minus 1. Huh? Okay, which also makes sense. You pay more first and then you deduct the savings, right, over there. And then we remember what the formula for this one was. What was that? It is just 1 over A1 plus A capital N minus K times. For this one we will have, I guess, AN. Was it AN? Did we write this somewhere? Right, so this is AN, right, for this one. And then you divide by the same denominator. So we have common denominator for both terms, like this. And then actually we can simplify it. So under the common denominator, in the numerator we now have C plus K minus K times AN. Right? So what did we quantify? If you decide to implement H replacement maintenance policy, right? This was a maintenance policy. And if you know that the costs that you are dealing with for a planned replacement is C, and the additional cost for an unplanned in-service failure, replacement because of an in-service failure is K, right? Then this is actually what? The total, well, this is the long run cost, long run expected average cost. If you decide to change, right? If you decide to implement a plant replacement at Hn. So what is the best n? Now you can at least just enumerate, right? For different n's, you can just construct a table for different n. Now you know the right answer. The cost is just this simple formula. You would just calculate, maybe draw the curve and just find the n which will give you the minimum. Right? Okay. That's how you will just find the optimal H replacement policy, right? So you can find the optimal H replacement policy, right? Is given by what? Given by n star which minimizes this formula, namely, right? So whether you construct a table or just plot it, whatever you do, this one, which minimizes this, right? Maybe I don't need this there then. All right? Any questions about this? All right, let us stop here then. I guess we can make a fresh start tomorrow. So tomorrow, what are we going to talk about? So up to today, all the Markov chains that we discussed, right? In all of them, we were told what the one-step transition properties would be. We did not have any control over them. But in certain problems, you will be allowed to take one of the alternative available actions which will actually allow you to change one-step transition probabilities. So unfavorable, you can make the probability of reaching unfavorable states in the future small by taking certain actions, but then there will be some costs associated with those things, right? If you cannot afford, then you may just live with actually actions that will perhaps increase the risk of reaching some unfavorable states in the future. And usually then you will try to find a way to choose the best actions so that in overall, whatever the costs involved, the long run, for example, expected average cost is going to be minimized. Right? So we are then we are going to find ourselves dealing with stochastic optimization problems where we are trying to control a stochastic process by basically taking certain actions that will eventually affect the one-step transition probabilities, which imply, which control, in fact, the likelihood that the process will actually be in some unfavorable or favorable states in the future. Right? So we will learn, for example, how to use linear programming to find so-called optimal strategies, optimal policies, and then we will discuss policy improvement algorithm. Right? These are alternatives for large problems. If you cannot run the linear programming, then you may consider using policy iteration algorithm, policy improvement algorithm, and so on and so forth. Okay? That's going to be the topic for tomorrow. Right? Hopefully we'll finish this thing tomorrow, and then we'll move to Poisson processes next week. Okay? All right, I'll see you tomorrow morning, right? 9:30, am I right? 9:40, or we'll start in 9:40. All right, I'll see you tomorrow then.